This lecture covers repeated games. So what's a repeated game? It's where we take a static game of complete information. For our purposes, we're going to use this game. And instead of it being a one-shot game, we're going to let our players play it over and over and over again. So we'll use this game. This will be our static game of complete information. Let's just talk about the static game itself first. We'll think back to our first 6 weeks. How can we find a Nash equilibrium in this game? We could underline best responses, or we could observe that this game has the structure of prisoner's dilemma. What's the Nash equilibrium? Escalate is strictly dominant for Yuk. Escalate is strictly dominant for Zook. So the unique Nash equilibrium in this static game of complete information is escalate, escalate. So when we studied prisoner's dilemma way back at the beginning of the term, we talked about the fact that it would be nice for the players, for Yuk and Zook, if there were some way that they could both play de-escalate. Because then each would receive 2 instead of each receiving 1, which is the payoff and Nash equilibrium to each player. But we observed that at least in the static version of this game, that wasn't possible because escalate is a strictly dominant strategy for Yuk, and escalate is a strictly dominant strategy for Zook. So even though at the end of the game, they've both escalated, they both receive 1 and think, oh, if only we both de-escalated. That's not stable in the sense of Nash equilibrium's requirements of stability. They're not mutual best responses. But what we're going to see when we start to let this game be a repeated game is that there is, in fact, a way to foster something that looks like cooperation. Cooperation that is selfishly motivated between these two once this game repeats infinitely. Basically because instead of this being a one-shot static game when this game is infinitely repeated, each player has not only today's incentives to worry about, but also tomorrow's incentives to worry about, the future incentives as well as present incentives. And so the goal of this study is to explore what those future incentives can do to strategies, and to write down what are called grim trigger strategies in which the threat of future escalation encourages present day de-escalation. And in fact, the subgame perfect Nash equilibrium path of play will be that both players de-escalate all of the time, forever. Okay. So we're at the top of page 18, or I guess in the middle where it says repeated games in the notes. Here's our static game of complete information. And now we're going to introduce some notation for repeated games. We're going to call this game G. So now we're going to have a little ordered triple. We're going to have 3 things. We're going to have G, a static game of complete information. We're going to have capital T. This is the number of repetitions. Number of repetitions of G. Okay. T should be less than or equal to infinity. Now I know writing equal to infinity is an abuse of notation, but it's okay. We do it. everybody says it's an abusive notation, but we do it, we are going to ultimately consider the possibility, indeed we're going to focus on the possibility, that G repeats infinitely many times. And last but not least, this delta. This is going to be just as in infinite horizon, alternating offer bargaining. This is the discount factor between periods. So another way to think about this is in the first round of this game, our players play G as shown over there. In the second round of this game, we multiply every number in that matrix by delta. In the third round of the game, we multiply every number in that matrix by delta squared, and so on. Okay. So we're going to use G delta T to denote G repeated T times with discount factor delta. Okay. And we're going to study, not this game, which we've studied already, but we're going to study this game, G delta, GT delta. Okay, delta as before, delta is in between 0 and 1. It's not 0, it's not 1. It's strictly in between. So it comports with our normal notion of a discount factor, and it's saying that payoff tomorrow is worth less than payoff today. It's better to get paid today. If you're following what the Federal Reserve just did, they just slashed interest rates. When the Federal Reserve slashes interest rates, they're saying we can wait longer to get our money back. We're willing to let the money be cheaper. We're willing to let you hang on for longer. They're saying we can be more patient. The discount rate the Fed's discount rate, they said, just got closer to 1. Or discount factor got closer to 1. Discount rate is a specific macroeconomic term. My apologies. Okay, so I know this has been a concern in the past, we are not going to follow the notes exactly here. We are not going to talk about average payoffs in the moment. We're just going to look at this game. We're going to let T be equal to 2. We aren't going to worry too much about delta. We'll just let delta be delta. We're just going to explore the effect of adding one more period, one repetition to this game, and seeing if we can get our players in equilibrium to de-escalate at some point. Now, the convention is that the first period is in fact called period 0. So our second period is going to be period 1. And so we aren't quite going to write down a tree, but it'll be close. So in period 0, there's no discounting. So our players play G, just as we see it over there. And then in period 0, we discount by delta. And I'm going to use Y for yuk, Z for zook, D for de-escalate, and E for escalate to avoid writing things over and over again. So we said in the next period we should discount. We're going to multiply every number in this matrix by delta. 0 delta is 0. 1 delta is delta. So here's our game. Our players play period 0, then they play period 1, and then the game ends. So this isn't quite a tree, but let's do what is in essence backwards induction. Here we are in period 1, the last period of the game. Yuk and Zook, this is for all intents and purposes a static game of complete information. They're going to play this game, and then the repeated game ends, because this is the last period. And Yuk will look at this situation and say, well, 3 delta is greater than 2 delta. 1 delta is greater than 0. So escalate strictly dominates de-escalate. De-escalate is a strictly dominated strategy. Zook will go through a similar line of reasoning. De-escalate is strictly dominated. 2 delta is less than 3 delta. 0 is less than 1 delta. So our players are going to play escalate, escalate. Okay. Now we come to period 0. We're working our way backwards through time. Both players know that in period 1, the last period, the second period of the game, they're both going to escalate the conflict. And so here, in period 0, the decision in period 0 is divorced from the decision in period 1. They both know what will happen in period 1. Both are going to escalate the conflict. So period 0, from a strategic standpoint, really is the same decision as period 1. They can't be rationally linked together. So, knowing that there's going to be escalation in the next period, Yuk and Zook look at this and say, well, I know we're both going to escalate in the next period no matter what, so it must be that the rational thing to do is to simply maximize my payoff in period 0, if possible, given my opponent's decision. And so the same argument applies. Yuk considers escalate versus de-escalate. De-escalate is strictly dominated. Zook, de-escalate is also strictly dominated. So we can eliminate these. And so what we've said is that the subgame perfect Nash equilibrium in this game, Yuk plays escalate, escalate. This isn't a strategy for Yuk and Zook. This is Yuk's strategy in period 0 and action. Action in period 0 and action in period 1. Here's Zook. Here is Zook's action in period 0, action in period 1. This is the subgame perfect Nash equilibrium. It's the only one. Here's Yuk's strategy, here's Zook's strategy. Now, there was nothing special about the fact that we picked 2 periods up here. We could have picked 3 or 7 or 152, some finite number. That's the important thing. And in the last period, however many periods there were, each player would know that that last period is equivalent to the original game. It's a static game of complete information. Escalate strictly dominates de-escalate. Both players escalate in the last period, which means both players escalate in the second to last period, and so on and so forth until we get to the beginning of the game. So as long as this number of periods is finite, the subgame perfect Nash equilibrium is going to be Yuk escalates in every period and Zook escalates in every period. Note that the delta, at least right now, is really irrelevant. The only important thing is it's between 0 and 1. It is positive, but it's not 0. And so the result is that in every period, escalate is a strictly dominant strategy if that period is just viewed in a vacuum. And the fact that we have finitely many repetitions means that indeed, each period is strategically in its own little vacuum. Okay, so this is not super interesting. This is just a repetition of the Nash equilibrium in the static game of complete information that we saw back in the first 6 weeks of class. The way that, what we said our idea was maybe if our players have some incentive, something that will happen tomorrow, I want my opponent to de-escalate the conflict tomorrow. If we always have a tomorrow to live for, then maybe those incentives will obtain and we'll be able to de-escalate along the subgame perfect Nash equilibrium path of play. But the thing is, if this choice of number of periods is finite, there's not always a tomorrow. There's some point where the world ends, as it were, or the game at least ends. So what we want to consider now is the case where a game is not finitely repeated, but infinitely repeated. All right. All right, so let's keep up our matrix game. Here it is. This is always going to be our underlying stage game. G is always going to represent this underlying stage game. But now what we want to do is consider the infinitely repeated game, which we notate G infinity delta. Here's our game, here's our number of periods. I know, it's not a number, but it will do. And here's our discount factor between periods. So there's one very boring subgame, perfect Nash equilibrium, in which Yuk plays escalate in every period and Zook plays escalate in every period. This is the same flavor as our subgame perfect Nash equilibrium in the one period game or in the finitely repeated game. So we want to see now if we can find a different subgame perfect Nash equilibrium, one in which our players de-escalate sometimes. Okay, so we're now at the top of page 21. And so what we want to do is introduce what are called Grimm trigger strategies. So note that these are just strategies. We're not saying anything yet about whether they form a subgame perfect Nash equilibrium or the conditions under which they form a subgame perfect Nash equilibrium. We're just writing down a strategy for each player. So the difference between this Grimm trigger strategy and some of the strategies that we've seen in other games is that it very explicitly, although we've done this, it very explicitly links past behavior, past actions, and future actions. So here's how we write this. So a strategy is a specification of an action, escalate or de-escalate, in each and every period. So here, we're going to let Yuk play the following strategy. Period 0, de-escalate. In periods 1, 2, and so on, here's how we're going to link past history, past actions by both Yuk and Zook to current play. If both Yuk and Zook play de-escalate in every prior period, then play de-escalate. On the other hand, if either Yuk or Zook played escalate, in any prior period, play escalate. Okay. All right, so here's a strategy. This is Yuk's strategy. This is also going to be Zook's strategy. Could be Yuk, could be Zook. We'll write this down from Yuk's point of view right now. So out of the gate, period 0, de-escalate. De-escalate the conflict. And then, after period 0, but before period 1, Yuk observes whether she de-escalated or not, and whether Zook de-escalated or not. So come period 1, if Yuk observed that both players de-escalated in period 0, then Yuk's strategy says, in that case, de-escalate. On the other hand, if either Yuk or Zook deviated, if either one decided to escalate the conflict, despite this instruction for period 0, if either one of them did that, if Zook escalated, but also if Yuk escalated, then escalate the conflict. What's so grim about this strategy? What's the trigger? The trigger is a prior escalation, and what's so grim about it? There's no way off the escalation path once they get going. Let's imagine that in period 27, there's been both players de-escalated up through the 25th round. Then in period 26, Yuk escalates the conflict. And then come period 27, despite all of that previous de-escalation, the rule is if there was any previous escalation, escalate the conflict escalates, and now in all future periods, there will have been previous escalation, so the conflict keeps escalating. Okay, so here's our strategy. We haven't said whether it's a subgame perfect Nash equilibrium or not. These strategies form a subgame perfect Nash equilibrium or not. We haven't said anything about the conditions under which they might or might not form a subgame perfect Nash equilibrium. But we have written down a rule for how each player can determine what to do, which action to take in every period. So now we want to consider the one thing that we haven't considered yet. We want to consider the role of the discount factor. So what we'll see is these strategies played by Yuk and Zook do form a subgame perfect Nash equilibrium if both players are patient enough. If both players are patient enough, waiting to get 2 in every future period rather than 1 in every current period is valuable enough that neither player will want to escalate the conflict and get 3 right away. So if delta is close enough to 1, and our goal is going to be to find what's called the critical delta, how close does delta have to be to 1? And that will depend on the underlying game G. Then the Grimm trigger strategies will form a subgame perfect Nash equilibrium. If, on the other hand, delta is not sufficiently close to 1, then players will not be willing to do that. Back to the Federal Reserve, they lowered interest rates. They're saying we can be more patient because what they don't want is people to pull their money out of stocks, bonds, banks, because they're concerned that something is going to happen to it. And therefore they would be safer holding physical cash. The Fed is saying we can wait longer for our money. We'll let the money stay out there. Don't worry, we'll provide enough money to shore up the economy. People are still nervous. Okay, so here's our Grimm trigger strategy. I'm going to erase it now. All right, so let's ask ourselves, what delta, how large does delta have to be for these strategies to form a subgame perfect Nash equilibrium? And so what we want to do is compare 2 things. The payoff on the equilibrium path This is the world where both players de-escalate in period 0. They both follow their Grimm trigger strategies. So in period 0, both de-escalate. And then in period 1, both players observe that in period 0, both players de-escalated. So in period 1, both players de-escalate again. In period 2, Both players observed that in both periods 0 and period 1, both players de-escalated. So in period 2, they both de-escalate, and so on and so forth. So we want to compare this payoff to the payoff on the punishment path. Or the deviation path. So this is the world, and there are many ways to deviate, but if a player is going to deviate from the Grim Trigger strategy, the player should deviate right away. The gain from deviating in period 0 is 1. 3 is 1 more than 2. But deviation in every later period, the benefit is discounted. So a player deviates in period 1, this is 3 delta minus 2 delta is only delta, which is less than 1. So although there are many deviation paths, we're only going to look at a path where one player deviates right away in period 0. And these strategies are going to form a subgame perfect Nash equilibrium if the payoff on the equilibrium path is at least as good, greater than or equal, to the payoff on the punishment path, or the deviation path. So the deviation path is where somebody wakes up in the morning, looks at his or her Grim Trigger strategy and says, the hell with it, and just decides to escalate anyway. All right, so let's write down what these are. We'll do this from Yuk's perspective, although it doesn't really matter since the game is symmetric. If they both de-escalate in period 0, Yuk gets 2. They both de-escalated. It's period 0. There's no discounting yet. Here's Yuk's payoff. Now, come period 1, both of them de-escalated in period 0 over here. So the Grim Trigger strategy says if both players de-escalated every prior period, de-escalate again. So Yuk gets another 2, but this is the second round of the game, period 1, so this payoff is discounted by delta. So this is 2 plus 2 delta. In period 2, the third round of the game, both of them de-escalate again. Both players de-escalated in period 0 and 1. So the Grim Trigger strategy says de-escalate in period 2, the third round, and so on and so forth. So we have a geometric series here. The constant ratio between terms is delta. 2 delta over 2 is delta. 2 delta squared over 2 delta is delta. 2 delta cubed over 2 delta squared is delta, so on and so forth. So this is the sum. We can write this in sigma notation. From t is equal to 0 to infinity of 2 times delta to the t. So when t is 0, this is 2 times delta to the 0, which is 1. We get 2. When t is 1, we get 2 times delta to the 1 is 2 delta, and so on and so on. Remember that when the constant ratio is has absolute value between 0 and 1, which delta does, it's between 0 and 1 itself. The sum of this geometric series is the initial term, 2, over 1 minus the constant ratio between terms. So the payoff on the equilibrium path is 2 over 1 minus delta. All right, so now let's consider the payoff on the punishment path, on the deviation path. What happens? Well, let's suppose that Yuk wakes up in the morning and says, the hell with it, I'll escalate. But Zook follows the Grim Trigger strategy, which says in period 0, de-escalate the conflict. So Yuk gets 3. All right. But now the Grim Trigger strategy says, if any player has escalated in the past, escalate. So in period 0, Yook escalated. So in period 1, both players will escalate. So now, in period 1, Yook gets 1. Both players escalated. Here we are. But this is period 1, so we're going to discount by delta. In period 2, again, the groom trigger strategy says if any previous escalation occurred by either player, escalate. So both players escalate. Yook gets 1 again. This is period 2, so we're going to discount by delta squared. Next period, again, they both get 1. Now we're going to discount by delta cubed. All right, and so on and so on. Let's write this using sigma notation. So 3 is out here all by itself. It's not part of our geometric series. Plus, this remaining piece forms a geometric series. The constant ratio between terms is delta. Delta squared over delta is delta. Delta cubed over delta squared is delta. So here we have delta times delta to the t. Let's check. If t is 0, delta to the 0 is 1, times delta is delta. If t is equal to 1, delta to the t is delta to the 1 is delta, times delta is delta squared. Okay. And so again, we can write this somewhat more neatly using our formula for the sum of a geometric series. Our initial term is delta divided by 1 minus the constant ratio. The constant ratio is delta. So here's the payoff on the equilibrium path. Here's the payoff on the deviation path, on the punishment path. There's a deviation, and then there's punishment for the rest of the game. Okay, so here's how to write down the payoff on these two paths. And so now, when do these strategies form a subgame perfect Nash equilibrium, these Grimm trigger strategies? We said they form a subgame perfect Nash equilibrium when a player's payoff from being on the equilibrium path is greater than or equal to our player's payoff from being on the punishment path, on the deviation path. So that will give us an inequality in terms of delta, and that will tell us how patient players need to be in order to, for these Grimm trigger strategies to form a subgame perfect Nash equilibrium. Okay, so on the equilibrium path, our player, Yook, or Zook as the case may be, gets 2 over 1 minus delta. On the punishment, deviation path, our player gets 3 plus delta over 1 minus delta. Okay. All right, so the last thing we need to do here is set up this inequality we just described. We said that the Grimm trigger strategies when this statement holds true, we figured out what these payoffs are on the equilibrium path. We have 2 over 1 minus delta. On the punishment path, or the deviation path, we get 3 plus delta over 1 minus delta. So we're going to rearrange this so that we have delta on one side and all the numbers on the other side. Okay, let's clear denominators. We're going to multiply through by 1 minus delta. That's fine. We're not accidentally multiplying by 0. We're definitely multiplying by a positive number because delta is between 0 and 1. Okay, now let's distribute this. Okay, minus 3 delta plus delta is minus 2 delta. So on this side, it's positive 2 delta. 3 minus 2 is 1. We'll come up over here. We're going to divide by 2 on both sides. Delta is greater than or equal to a half. The Grimm trigger strategies with this particular underlying stage game form a subgame perfect Nash equilibrium whenever the delta is greater than or equal to a half. Delta isn't anything that anybody chooses. It's just some sort of, unless you're the Federal Open Market Committee, it's just an underlying parameter of the game. This number on the right is what's called the critical delta. Players need a delta greater than or equal to a half in order for the Grimm trigger strategies to form a subgame perfect Nash equilibrium, in the sense that players will actually want to stay on the equilibrium path, and they'll de-escalate in every period. If delta drops lower than a half, the Grimm trigger strategies stop forming a subgame perfect Nash equilibrium, and our players will prefer to escalate the conflict in every period. So if you think about two countries that are trying to negotiate, patience really is a virtue. If countries are patient, they can keep talking to each other, they'll succeed in de-escalating a conflict. If the countries are impatient, you'll start to see a little bit more escalation. If you think about the US and the Soviets back during the Cold War, they figured out a way to be patient enough. It was difficult, they weren't always maybe as patient as optimal, but they figured out a way to be patient. The underlying patience parameter was somewhat above the critical delta. If you think about the US and China right now, although we are, I hope, not close to a hot war, we have figured out so far how to be patient enough. You could argue that the tariffs are a sign that the US has become less patient. If you think about China and Taiwan, China thinks Taiwan is part of Taiwan. Taiwan thinks it's its own country. The US approach is what's called the one China policy. We don't acknowledge Taiwan as a separate entity, but we also, by the same token, would not approve of China attacking Taiwan. China and Taiwan have figured out how to be patient, because there's in fact a lot of traffic between the two land masses, between Taiwan, the island, and China, mainland China. Okay. We can think of this as a measure of how patient. Saudi and Iran are perhaps very close to the critical delta. They haven't fought a hot war, or at least they're not fighting one right now. However, they're certainly fighting a proxy war. Although we don't model that here, you could imagine escalate to hot war, a third strategy that's fight a proxy war, and this one that says de-escalate the conflict. But we can think of this delta as how close you are to conflict. All right. So this is how to write down Grimm trigger strategies, how to figure out the critical delta. It will depend on whatever the underlying stage game is. All right, so this has been a very algebraic interpretation. The next lecture is going to talk about the Folk theorem. Here, We said we can write down a Grim trigger strategy in which the equilibrium path has both players de-escalating in every period. But it's going to turn out that there's a large family of Grim trigger strategies, and with each Grim trigger strategy, there's an associated critical delta that allows those Grim trigger strategies to form a subgame perfect Nash equilibrium. And the Folk theorem is going to provide a geometric interpretation of that.